So to start off with, let's have a look at what we're going to deal with. There are quite a number of topics that we have in this area, and the first thing we're going to do is define what probability is. Then we're going to look at how probability is expressed. We'll look at some terminology so that you know the kinds of terms that we use when we're speaking of probability. We'll also look at what is statistical probability versus theoretical probability. And of course, we'll have to do a number of examples so that you can get your hands onto doing some of the work that is required. Then we'll cover the probability associated with recurring outcomes, or outcomes that happen time after time. And lastly, we'll do something called tree diagrams. We'll see what those are in a moment. Now, to define probability. Probability is that branch of mathematics that deals with the idea of chance. And, you know, people speak in language, they say things like, oh, there's probably about a 50% chance that it's going to rain today, or I have a 10% chance of winning that competition. Well, how do they know that they have a 10% chance or a 20% chance or whatever the percentage is? How do they work it out? Is there a way of working it out? Well, probability does deal with this exact question, and we're going to see how we can mathematically work out what the chances are of things happening. Particularly, the branch of mathematics is used in things like predicting the weather. The weather is always associated with a chance relationship. You'll see if you watch television and you're looking at the news and maybe the weather comes on afterwards, you'll say that there's a 60%, you'll see that they'll say there's a 60% chance of rain or 30% chance of rain. And how do they know these values? Well, they've actually done some mathematical models to work out what the chances are of whether it's going to be a certain kind of weather at any time. So the weather industry uses it, then also the insurance industry, because they're working with chance all the time. They want to know, for example, what are the chances of someone who's maybe 30 years of age, who's just got their license and had it for 3 years, having a car accident? Because based on those chances, they will then set up an insurance premium for people who want to take out insurance against car accidents. And the insurance industry in South Africa is quite a large industry and relies heavily on chance or probability being accurately expressed mathematically. And they'll pay people who do mathematical work on chance or probability, they'll pay them a lot of money so that they can get a good reflection of what the chances are that certain events will happen. And of course, chance is probably most easily expressed in the gambling industry, where the games of chance that are being played are also mathematically calculated so that the casinos and the people who are operating them want to know exactly how much money they're going to end up getting out of the people who play those games based on the chances of them winning those games. It would be a disaster for any casino if the chances of winning were far better than the chance of the casino actually making money. Of course, that never really happens in real life because, again, they have chosen probabilities for these games in such a way mathematically that they know that they're almost guaranteed to win just every single time. So let's have a quick look at how we're going to express our probability. You'll see we have a nice straight line here, and if I put on the one side of the line, let's just draw a line here, and let's say we've got a 0 chance of winning over here, and on this side we have a 100% chance of winning. See, this is the scope of what probability will use. If I've got a 0 chance of winning something, it means it's impossible. I'll never win it, okay? There's just 0% chance of winning that thing. So let's write here, impossible. Well, then what would we write on the other side? Because if something is 100% sure, and I know it's going to happen, and I've got a 100% chance of maybe winning that iPad in that next competition, whatever it is, what would happen? What would we call that? Well, a 100% chance we'll call a certainty. So anything in between that, in between impossible and a certainty, we can express as some kind of figure. Notice we couldn't go beyond the zero. We can't have something that is less than impossible, okay, or more impossible for want of a better term. That doesn't make sense. If something's impossible, that's all there is to it. It's impossible. So 0% or zero is our bottom limit when we're discussing probability. By the same token, we can't have something that's more than 100% possibility of being 1. If something is certain, that's all there is to it. It can't be more certain. So it couldn't have 120%, for example, of winning something. That's just never going to happen. So when we're talking in percentage terms, of course, we'll use the values 0 to 100. If we go on to the next explanation, it says when we talk about the chance of something occurring, we usually talk about the percentage. That's what we've been saying earlier on, chance of something occurring. That's what I said earlier, 50% chance of something happening, 20% chance of something happening. But we really have three mathematical ways of expressing probability. So the first one we've already seen, that's the percentage. We're also going to express it as a decimal. And we'll have a look at that in a moment. And then lastly, another way that we're going to see probability very often is as a fraction. Remember, a fraction is written as two numbers over each other. Something, for example, like a quarter. And then just to give you an idea of a decimal, let's put 0.5. So these three ways or methods of describing probability are all going to be used almost interchangeably in your examinations. Just as a point of noting here, you can actually use either of them or all three of them when you're expressing probability in your answers. You can leave it as a percentage, you can express it as a decimal, and you can express it as a fraction. Just going back to that page where I drew the line, let's just go and have a quick look there. We had the percentages 0 to 100 on our line. If we were to use a decimal, then we would have a value between 0 and 1. So as a decimal, 0 would mean an impossibility, and 1, a value of 1, would be a certainty. Any value in between, something for example like 0.1 or 0.2, would express a certain percentage of probability. Lastly, as a fraction, and we can also do this, we can just put fractions here, 0 over any number, let's take 4 for example, 0 over 4 would express a 0 probability or an impossibility again. And lastly then, as a fraction on this side, we could have 4 over 4. And 4 over 4 would simply be a certainty, because that would express a whole or a 1 again. So either of these values can be used on our continuity line from 0 to 1 or 0 to 100%. And there we've just got our answers. You can see the limits of the numbers in probability are as follows. As a percentage, let's just fill them in, 0 to 100%. You cannot have less than 0% and you cannot have more than 100% when speaking of probability. As a decimal, the values are 0 to 1. And then lastly, as fractions, well, you could choose any fraction and you could say 0 over, let's make it 10 this time, and that would then go to 10 out of 10. Again, you couldn't have something that said 11 out of 10, for example, as a fraction, because that would be something that would fall outside of the range of probability. Right, so let's have a quick look at some terminology now. There are words that you're often going to hear when being taught about probability. And the first one is the word an event. Now it says here, an event refers to something that can take place. Well, I'm sure you've heard this word in English before. An event can be anything that happens. When we talk about probability, we could use an example, for example, tossing a coin. If I took a coin out and I threw it over here, that would be an event. I'd say I'm going to throw a coin. And we could let that event happen once, maybe twice, or even 10 times in a row, and we could see what happens. So the event is the actual occurrence of something, and then the outcome refers to the possible results of any event. So looking back at my coin, if I took my coin, what are the possible things that could happen if I throw that coin? Well, the coin could either land on heads or tails. I'm sure you'll agree that for the coin to land on its side, and I usually get this question in my classroom, what if the coin doesn't land on heads or tails? Well, again, the probability of that happening would probably be very close to zero or impossible. Just given a fair coin, we'd expect it to land on either a heads or a tails. So the event is the throwing of the coin. The outcome of that event is, would it land on heads or would it land on tails? Here again, just to recap, an outcome that has a 100% chance of occurring is known as a certainty. And an outcome that has a 0% chance of occurring is known as an impossibility. So if I was throwing my coin, and say I had a coin that had 2 heads, well, what would be the probability of that coin landing on heads? Well, throwing the coin, it has heads on both sides. So it's always going to land on either heads or heads. So it's a certainty that that thing will land on heads. What if I then said to you, well, then what's the probability of this coin that has 2 heads on either side landing on tails? Well, there are no tails on either side of the coin, so it would be an impossibility for that coin to actually land on tails. And of course, if you were playing a coin game and the other person didn't know that this was a 2 heads coins and you called heads every time and you kept winning, they might start getting a little suspicious and want to see the coin. Because you're almost certain of, or you are certain of winning every single time, and they're certain of losing every time, or it's impossible for them to win because they're calling tails and there are no tails on that coin. All right, so let's have a look quickly now at statistical versus theoretical probability. And then we'll get into some examples just after that. Now, statistical probability refers to the experiment being done and to seeing the number of outcomes that occur for a specific set of events. Let's start with our coin probability again. If I took a coin here and I said to you, and you can go and do this example at home, take the coin and throw it 50 times. And each time you do, record what comes up. Well, let's start off. We throw the coin. Let's say it came up heads. Then I'd mark on my page. I'd say, right, we've got heads. Next time I throw it, it comes up tails. Next time, tails. And so we go on. Tails, then heads, then heads, then tails, then tails, tails. And we do this 50 times. At the end of the experiment, we'd say we've thrown the coin 50 times, and we'd want to say, well, how many times did it come up heads and how many times did it come up tails? Let's say, for example, it came up 26 times heads and 24 times tails. That would mean that statistically, this coin lands 26 out of 50 times it lands on heads, and 24 out of 50 times it lands on tails. If I wanted to, I could turn this into a percentage simply by multiplying the two numbers by 2, because that would give me something out of 100, and remember, a percentage is something out of 100. So that would be 52% of the time, it came out heads, and 48% it came out tails. This would be the result of my experiment. I could go and throw that coin again and maybe do it another 50 times and keep measuring and see if my probability remains the same. The chances are that it probably will, or be quite similar. But let's have a look at this other word now, which is theoretical probability. Now, theoretical probability lists the possible outcomes of any event and assigns a likelihood of the outcomes for each event. So what we're saying over there is, again, let's use our coin because that's a nice simple example. If I throw the coin, what are the possible outcomes for the coin? Well, it's heads and tails. There's only two possible outcomes for this coin, so we can only have heads or tails. Now, there are two events that could take place. I could throw the coin and I could get one of them could be heads, one of them as an outcome of tails. So that means that 1 out of 2 possibilities exists for heads and another 1 out of 2 possibilities exists for tails. For the outcome to be heads, I have 2 choices for that event. It can be heads or tails. And for the outcome to be tails, I also have 2 choices, heads or tails. So the probability here is 1 out of 2 for each of those, or if I write it as a percentage, 50% in each case. Now, you can see that the statistical versus the theoretical in this case were different. Remember, my statistical probability of getting heads turned out to be 52%. For tails, it was 48%. Just something as a matter of point here is, notice that both of these must always add up to the 100%. Something has gone wrong if you don't get 100% for the total. But since these two values are different, does that mean that I have a different probability for this coin? Well, yes and no. Theoretically, we can see the coin must land on 50% of the times heads and 50% tails. But in real life, that doesn't always happen. That's why with that experiment, I was testing the coin to see what it would do. And I can see that this coin actually lands 52% of the time on heads and only 48% of the time on tails. Let's use just another example to explain why this is important to do. If I took a dice, little cube with numbers on it, 1, 2, 3, and you know on the other side is 4, 5, and 6. Now, throwing a dice, what are the probabilities of the dice landing on any specific number? Well, there are 6 possibilities. The dice can land on 1, 2, 3, 4, 5, or 6. And again, theoretically, I would expect all of those to be equal. So I would take 100% and I would divide it by 6 to find the probability of each one. And of course, if we do that, let's just do that on a calculator quickly. 100%, because that's for all the events to happen, we'll divide that by 6. And we get an answer of 50 over 3, or a decimal of 16.6 as a percentage. Or if we wanted to make that as a decimal, we'd have to divide by 100 again. An answer of 1/6 as a fraction, or as a decimal as 0.166. So let's put that quickly on our sheet here. So there is a 1/6 chance of this dice landing on a 1. And there's a 1/6 chance of it landing on 2, 3, 4, 5, or 6. If I add all of those up again, they must come out to 100% or 6/6 or 1, using my different expressions of probability. So the dice has a 0.166 decimal, or a 16.6% chance of landing on any one of those 6 numbers. That's the theoretical possibility. But what if I threw the dice now and I did an experiment and I calculated the statistical probability and I found out the following? 1, 2, 3, 4, 5, 6. What if I found out, and let's say we did this and we threw the dice 100 times, and I found out that, okay, for 1 it came out 16, for 2 it came out 17, For 3 it came out 16. For 4 it came out 5 times. For 5 it came out, let's make it 20 times. And if we add up these numbers, we get 20 plus 5 is 25, plus 16 makes it 36. 46 and 7, that gives you 53. 63 and 6 gives you 69. That means at the end here, you've got a value of 31 for the 6. You can see that this dice doesn't seem to be working like it should. I should have a fair chance of landing on the same numbers. In 100 throws, it should be around 16 or 17 for all of them. But in this case, it wasn't. The 6 seems to land many, many more times than the other. Well, if a factory was making dice or die, and it was wanting to test that die to see if it was a fair dice, it would throw 100 times, maybe 1,000, maybe even 10,000 times. And they'd usually get a machine to do this, not a person. But if the dice came out with a very high number for one certain number, that dice would be considered loaded or unfair. And so they'd have to test, and casinos are very particular about this when they get dice for their games. They want to make sure those dice are going to land fairly, because the last thing they want to be accused of is cheating people. So they would need fair dice. So that would mean that the statistical probability must measure very closely to the theoretical probability for that dice to be allowed to go and be used in a casino. A dice that ended up doing what this dice did in our statistical experiment would certainly not pass the test for quality and would be considered a loaded dice or an unfair dice. Can you see how statistical probability does not necessarily mirror what should happen theoretically? And it is only in doing a statistical experiment that we can determine whether the theoretical probability is correct for that event to occur. And if the statistical probability is incorrect compared to the theoretical probability that we would expect, we would need to go back and ask the question why, or say something like, for example, in the dice experiment, that dice is not a fair dice. Something has gone wrong with it. It is weighted towards one side. And then we'd have to discard that dice and throw it away. Great, we're going to take a short break at this stage, and then we'll be back in a moment. So go and get yourself something to eat or drink, relax for a few moments, and then we'll continue this session.